Hi, I'm Nick Reinhardt, and today I'll talk to you about our work on deep imitative models. Let's say that we would like to learn a complex task, like driving a car. We could collect a lot of data from human drivers, which could help us learn this task. But what should we extract from the data? We could simply imitate the human drivers. Imitation can work when the model's prediction aligns exactly with what we want the robot to do. What if we want the robot to do something different, like navigate to this goal region? We can't directly apply imitation learning in this case, as the estimated likeliest human behavior may not align with the task. A model learned via imitation learning is difficult to direct to new tasks. However, imitation learning has the benefit of not requiring a reward function to specify behavior. If instead we consider learning a predictive model and plan under it, as in model-based reinforcement learning, the method can adapt its plans to different tasks using a provided reward function. However, it relies on the ability of the practitioner to design the reward function, which is very difficult to do in complex settings like autonomous driving. The key idea behind our work is that we can use data to constrain a model-based reinforcement learning method so that it only plans paths that are similar to those that the human demonstrators would have used. In the driving scenario, this means that the human drivers teach the model about the rules of the road, while model-based planning enables it to reach the desired test time goal. To use a deep imitative model, a data set of expert data is collected first. Then the model is trained to forecast expert behavior, conditioned on information about the scene. In our application, we use past states and LiDAR information to condition the model. A key aspect of this model is that it can evaluate the density of arbitrary trajectories, which enables us to use this density score as part of the optimization criterion during planning. After the model is learned, tasks are specified to the model in terms of functions of trajectories. For example, an indicator function on the final state of the trajectory tells the robot its goal is somewhere in the large orange region. The task and the model together define the optimization criterion that's used to plan what it thinks the expert driver would do to achieve this task. Here we see the resulting plan turning left, following the course directions of the task specification, while determining the fine-grained details according to the model of expert behavior. As long as the task can be specified as a function of a trajectory, then we can apply a deep imitative model to it. Here, the task is to navigate to one of several goal positions while avoiding potholes specified as a cost map. The best plans look as expert-like as possible while still achieving the joint objectives of avoiding potholes and navigating to a goal position. We perform planning as inference of a distribution that measures the probability of the plan given the goal in the scene. By applying Bayes' rule, we receive two relevant terms. The first is where we use the imitative model as a scene condition prior, and the second is the goal likelihood, which specifies the task objective. Let's take a look at some example goal likelihoods. Goals can be specified as constraints on positions of the trajectory. For instance, we may constrain the final position in the plan to end at one of many states. You can think of these states as being outputted by some higher-level path planning system like Google Maps. The system is not aware of other cars on the road, the state of the stoplights, or the precise position of the curb. It just provides a higher-level direction that includes which way to turn at each intersection. Instead of individual positions, we may constrain this trajectory to end along a line segment. As shown before, we can specify that the trajectory must end within a particular region. Here the plans avoid the potholes as specified by the cost map to arrive at a goal, while still otherwise moving as expert-like as possible, such as steering back into the correct lane after it avoids a pothole. We applied many variants of our method to perform receding horizon control in the CARLA simulator. The goal positions come from CARLA's A-star planner that uses the map to plan to a faraway destination. We observed and quantified our approach's robustness to poorly specified tasks, such as navigating given goals on the wrong-hand side of the road. We observed that it was often able to plan to these goals without violating the rules of the road that it internalized during training. Many variations of our method outperform a model-based reinforcement learning approach and prior imitation learning approaches on the CARLA dynamic navigation benchmark. Our method outperforms the best prior work on test data by more than 20% in terms of absolute performance, and it's flexible to many different types of task direction. Thanks for listening.